Every atom in your body holds the ghost of a long-dead star. This is the epic story of cosmic alchemy, the violent and beautiful processes that forged the very elements of life. By the end of this journey, you will understand exactly how the universe built the building blocks for everything, including you. We will travel back to the Big Bang and witness how stars became titanic element factories, only to tear themselves apart in supernova explosions. How did the iron in your blood come from a stellar catastrophe? What cosmic violence was needed to create the gold in a wedding ring? This story connects you directly to the grandest events in the cosmos. What does it mean to you, knowing you are literally made of stardust? The universe began in a state of unimaginable heat and density. For a fleeting few minutes, everything was hot enough and dense enough to cook up the very first atomic nuclei. This frantic burst of creation, known as Big Bang Nucleosynthesis, forged almost all the hydrogen and helium that would ever exist. A tiny sprinkling of lithium was also created. And then it stopped. The universe continued expanding, cooling so rapidly that the nuclear reactions simply froze solid. The cosmic kitchen had closed for business after producing only the 3 lightest ingredients. What was left was a vast, dark, and profoundly simple cosmos. There was no carbon, no oxygen, no iron. There were no planets to orbit stars, and no chemistry complex enough to build a single living cell. The universe was a sparse sea of primordial gas, waiting in the dark for billions of years. All the necessary drama, all the violent processes needed to build a more interesting reality, were still to come. The stage was set, but the main actors, the stars, had yet to make their entrance. But that dark, simple cosmos held a hidden potential for change. Deep within colossal clouds of that primordial hydrogen and helium, a silent force began to exert its will. Gravity, the great architect of the cosmos, started its patient work. It pulled wisps of gas together, drawing them into denser and denser knots. As more and more matter collapsed inward, the pressure at the center of these clouds grew unimaginably intense. The temperature skyrocketed until the core became a furnace hot enough to ignite the universe's most fundamental power source, nuclear fusion. In a brilliant flash of cosmic light, a star is born. This newborn star, like our own sun, settles into a long, stable life astronomers call the main sequence. At its heart, a relentless engine roars to life. It smashes hydrogen nuclei together with such force that they fuse, creating a new element, helium, and releasing a torrent of pure energy in the process. This outpouring of power creates a constant outward push, a force that perfectly balances the star's own immense weight, the crushing inward pull of its gravity. For billions of years, this delicate standoff can continue. The star burns steadily, a beacon in the dark, but it is also a factory. It is taking the simplest raw material left over from the Big Bang, hydrogen, and forging it into something new. This stable, long-lived phase is the first and most crucial step in the entire elemental production line. It is here, in the heart of an ordinary star, that the universe learns to build. Deep within the stellar core, a relentless subatomic dance unfolds. This is the proton-proton chain, the primary engine for stars like our own sun. Under unimaginable heat and pressure, simple hydrogen nuclei, which are just single protons, are forced together. They do not want to merge, their identical positive charges fiercely repelling each other. But the star's immense gravity creates conditions so extreme that it overcomes this natural aversion. In a rapid series of collisions and transformations, 4 hydrogen nuclei are ultimately forged into a single, new nucleus of helium. With every single fusion reaction, a tiny puff of pure energy is released, a direct conversion of matter into power. This is the profound truth of Einstein's famous equation, E equals mc squared, in action. A minuscule amount of mass is annihilated, transforming into the colossal outpouring of light and heat that floods the cosmos. This single process, repeated countless trillions of times every second, is what makes a star shine. It is a beautifully efficient and stable way to generate energy, allowing a star to burn steadily for billions of years. Yet for all its power, this stellar engine has a fundamental limitation. It only knows how to build two things, hydrogen and helium, the cosmic recipe for everything else. For the carbon in your bones or the oxygen you breathe requires a far more dramatic and desperate kind of stellar environment. This stable existence is a beautiful illusion, a temporary truce in a cosmic war. A star lives its entire life balanced on a knife's edge, caught between two opposing titanic forces. On one side is gravity, the relentless inward pull of the star's own immense mass, constantly trying to crush it into a tiny point. Pushing back is the tremendous outward pressure generated by the nuclear furnace in its core. This perfect, stable standoff is known as hydrostatic equilibrium, and it is the single most important factor in a star's long and stable life. It is this very balance, however, that contains the seeds of its own destruction and the birth of new elements. The star is like a meticulously controlled nuclear reactor, where the rate of the fusion reactions is perfectly tuned by the force of gravity itself. If the core ever slightly cools, gravity compresses it, raising the temperature and pressure, which forces the fusion reactions to accelerate, pushing back outwards. If the core gets too hot, it expands, which slightly cools it and slows the fusion rate, allowing gravity to pull it back in. This self-regulating system is why a star like our Sun can shine so steadily for billions of years. But this stability is entirely dependent on the star having a continuous supply of hydrogen fuel in its core. What happens when that fuel finally begins to run out? The delicate balance is broken and the star is forced to evolve, to change, and in doing so, it begins to forge the heavier elements that make our world and us possible. The star's stable life is a race against its own fuel supply. Deep in its core, the hydrogen that has powered it for billions of years is finally running out. The last embers of hydrogen fusion flicker and die. Instantly, the delicate balance that defined its existence shatters. With no outward pressure from fusion to hold it up, the star's own immense gravity becomes an unstoppable force. It begins to crush the core with unimaginable power. This collapse is not a gentle settling, it is a violent, runaway compression. The temperature and pressure in the core skyrocket, soaring to levels far beyond anything the star has ever experienced. The core becomes a hellish crucible, heating to over 100 million Kelvin. At this staggering temperature, a new and more powerful nuclear fire is ignited. The star has begun burning helium. This is not a simple transition, it is a dramatic rebirth into a far more volatile state. The star is no longer just a beacon, it is becoming a true elemental forge, and its first new creation will be the most important one of all, the foundation of life itself. Inside this superheated core, a frantic and improbable nuclear dance begins. It is called the triple alpha process. Individual helium nuclei, also known as alpha particles, are now moving with enough energy to overcome their mutual repulsion. The process is incredibly delicate. First, two helium nuclei collide and stick together, forming a highly unstable, fleeting nucleus of beryllium. This beryllium isotope exists for only a minuscule fraction of a second before it would normally tear itself apart. But in this extreme environment, a third helium nucleus can slam into the temporary beryllium before it has a chance to disintegrate. This three-way collision forges a stable, new atomic nucleus, carbon. This is a cosmic milestone of profound significance. For the first time since the Big Bang, the universe has created an element capable of forming long, complex chains and rings, the essential backbone of all known chemistry. Without carbon, there would be no proteins, no DNA, no sugars, and no life. The star has just built the most versatile Lego brick in the entire cosmos. For stars more massive than our Sun, the elemental production line does not stop there. The core, now rich with this newly forged carbon, can be compressed and heated even further by the star's relentless gravity. If the temperature climbs high enough, another helium nucleus can be fused onto a carbon nucleus. This collision creates a new, heavier element, oxygen. With these steps, the star has fundamentally transformed. It has graduated from a simple factory that only processed hydrogen into a sophisticated multi-stage industrial plant. It is now building the two elements most vital for life as we know it, carbon and oxygen. The star is layering itself like an onion with a core of carbon and oxygen, surrounded by a shell of burning helium, which is itself encased in an outer envelope of still burning hydrogen. Each layer represents a different phase of the star's life and a different stage of elemental creation. But for the most massive stars, this is merely the beginning of a much more dramatic and violent journey into the periodic table. The furnace must grow even hotter to forge the elements that come next. Yet for the most massive stars, the proton-proton chain is not the only way to burn. There exists a far more potent and efficient nuclear pathway, one that transforms the star into a high-speed engine for life's essential elements. This is the carbon-nitrogen-oxygen cycle, or the CNO cycle for short. In stars significantly heavier than our Sun, the cores burn so ferociously hot that this cycle takes over as the dominant power source. It works in an almost magical way, using pre-existing carbon, nitrogen, and oxygen not as fuel but as nuclear catalysts. Think of it like a sophisticated factory assembly line. A carbon-12 nucleus acts as a workbench. A hydrogen nucleus, a proton, fuses with it, transforming the carbon into a different element, nitrogen-13. This new nitrogen isotope is unstable and emits a positron and a neutrino to become carbon-13. Then another proton smashes in, turning it into stable nitrogen-14. The process continues with two more protons fusing in, first creating an unstable oxygen-15, which decays back to nitrogen-15. Finally, a fourth proton arrives, but this collision is different. It causes the nucleus to split, ejecting a brand new helium nucleus while perfectly regenerating the original carbon-12 workbench. The cycle is now complete, ready to begin again. The carbon, nitrogen, and oxygen are not consumed in the end. They are simply reshuffled and reused, but in this reshuffling, something profound happens. The cycle spends most of its time in the form of nitrogen-14. This means that over the star's lifetime, it actively concentrates nitrogen, a vital component of amino acids and DNA within its core. This alternative fusion path does more than just power a brilliant giant star. It acts as a cosmic refinery, enriching the stellar interior with the very seeds of future biology. It is a different, more elegant road to complexity, one that prepares the essential ingredients for life on a grand and explosive scale. This layered stellar architecture is a ticking clock. Deep within the massive star's heart, the factory floors are stacked one atop another, each operating at a fever pitch. In the outermost shell, hydrogen fuses into helium, just as it did for billions of years. But descend one layer inward, and you find a shell where helium is actively being forged into carbon and oxygen. Go deeper still, and the temperature soars enough for carbon atoms themselves to begin fusing, creating new elements like neon and magnesium. Further in, oxygen fusion ignites, producing silicon and sulfur. Each step inward is a descent into a more infernal realm, with temperatures and pressures climbing to truly incomprehensible levels. Each shell is a dedicated workshop, its output determined by the specific fuel available and the brutal conditions required to ignite it. This entire complex structure exists in a state of precarious balance, a temporary equilibrium maintained only by the furious energy output of each successive layer. But this frantic, multi-stage production line has a final, definitive product. At the very center of this cosmic onion, in the innermost core, the final elemental ash is collecting. Through a final series of fusion reactions, silicon and sulfur are fused together, and the ultimate element is forged, iron. The creation of iron is a cosmic turning point, a moment of profound and terrible significance. For the first time in the star's long life, the nuclear fires have produced an element that cannot be used as fuel. Fusing iron does not release energy, it consumes it. The star's central engine, after billions of years of brilliant service, has just run out of gas. The star has been building its own tomb, an iron coffin at its very center. This inert iron core begins to grow, silently stockpiling at the heart of the star, while the surrounding shells continue their frantic burning, unaware that the foundation is about to give way. All the diverse elements created in these layers, from the oxygen in the outer shells to the neon and magnesium nearer the center, are now trapped, their fate tied to the impending doom of the iron core. The star has spent its life building an incredible inventory of atomic wealth, and it is about to make the ultimate withdrawal. Iron has become the ultimate cosmic dead end. At the very center of this massive, layered star, an inert core of iron has been growing in silence. The iron nucleus is special. It is the most stable arrangement of protons and neutrons in the entire universe. This stability is its curse, for all the other elements fusing them together released a burst of energy that powered the star. But forcing iron to fuse actually consumes energy. It saps power from the system. So when the core finally becomes solid iron, the central fusion engine does not just slow down, it shuts off completely. The star's heart stops. In that single, silent moment, the balance of power shifts for the final time. Gravity, held at bay for millions of years, now has nothing to push against. It wins. The result is one of the most violent events imaginable, the Iron Catastrophe. In less than a second, the star's core, a sphere of matter once roughly the size of our entire planet, is utterly crushed. It collapses inward at a significant fraction of the speed of light, compressing down into an unthinkably dense ball only a few dozen kilometers across. The collapse is so rapid and so violent that it sends a powerful shockwave rebounding outward through the entire star. This is not the end of the story, however. It is the violent, necessary prelude to the universe's most creative and destructive act. The star is about to die, but in its death throes, it will become the ultimate element factory, forging nearly every atom in your body in a single, glorious, and catastrophic explosion. The star's iron heart collapses, and the silence that follows is the most deceptive in the cosmos. Then the entire structure rebels, a cataclysmic rebound shockwave, born from the core's unimaginable compression, rips outward at hypersonic speeds. It does not gently push the star's outer layers away. It utterly blasts them apart in the most violent spectacle known to nature, a supernova explosion. For a few glorious weeks, this single dying star can shine brighter than every other star in its entire galaxy combined. It is a cosmic beacon of both death and creation. Within this expanding fireball, a maelstrom of energy and a flood of subatomic particles create conditions far more extreme than the star's core ever was. This is where the true cosmic alchemy happens, where the final, heavy ingredients of the periodic table are forged. The key to this final act is a frantic process known as rapid neutron capture, or the Are process. In this unimaginable environment, atomic nuclei are bombarded by a dense wave of free neutrons. They do not have time to stabilize, to undergo their normal radioactive decay. Instead, they are forced to swallow neutron after neutron after neutron, bloating into heavier and heavier, highly unstable forms. Almost instantly, these overstuffed nuclei begin to decay, settling into stable, brand new elements. It is in this frantic, chaotic blizzard of particles that the universe forges the elements that were forever out of reach for the star's internal furnaces. Gold, the treasure of kings and the heart of jewelry, is born here. Silver, uranium, and even the iodine that is essential for your thyroid function, all are created in these final, violent moments. The supernova is the universe's ultimate sacrifice and its greatest gift. In its self-destructive fury, it scatters this newly forged atomic wealth far and wide, ejecting it at tremendous speeds into the dark, waiting interstellar space. These stellar ashes, rich with oxygen, carbon, iron, gold, and every other element, will eventually mix with primordial hydrogen and helium. They become the raw material for new generations of stars, for planets, and for oceans. Every rocky world, every mountain range, and every living thing is built from the debris of these ancient stellar cataclysms. But this elemental creation story is not yet complete. We have seen how stars build elements up to iron, and how supernova forge the heaviest atoms in a single, violent flash. Yet there is another, more patient path to complexity, a slower, gentler alchemy that works alongside the stellar explosions. To build the entire upper half of the periodic table, from the copper in electrical wiring to the uranium that powers reactors, the universe employs two distinct assembly lines. The first is the slow neutron capture process, or the S process. This occurs deep within the calm, vast interiors of aging red giant stars. Here, in the relative tranquility between stellar catastrophes, atomic nuclei drift through a sparse sea of free neutrons. They occasionally capture one of these neutrons, which slightly increases their atomic mass. This newly formed, slightly heavier isotope is often unstable. But in this slow process, there is time, often years or even centuries, for that unstable nucleus to settle down, to undergo radioactive decay and transform into a stable, different element before it captures another neutron. It is a methodical, step-by-step walk up the periodic table, a patient building process that creates about half of the elements heavier than iron, like strontium, barium, and lead. The second path is its utter opposite, the rapid neutron capture process, or the Are process, which we glimpsed in the supernova's heart. This is a frantic, chaotic blizzard of neutrons. In the unimaginable density of a collapsing stellar core or the debris of colliding neutron stars, atomic nuclei are bombarded. They have no time to decay. In mere seconds, a single nucleus can be forced to swallow dozens of neutrons, bloating into an extremely heavy, wildly unstable form. Only after the storm subsides does this overstuffed nucleus have a chance to calm down, decaying through a series of steps into stable, precious elements like gold, platinum, and uranium. These two processes, the slow and the rapid, leave behind distinct forensic signatures in the atoms they create, like different factory stamps on the same product. Their combined output fills in every remaining box on the periodic table, providing the full suite of chemical ingredients the universe will ever need. This cosmic debris does not simply vanish into the endless dark. The remains of that ancient supernova, a chaotic cloud of incandescent gas and stardust, slowly expands and cools. Over millennia, it coalesces into one of the most beautiful structures in the cosmos, a nebula. These vast, glowing clouds are far more than just celestial gravestones. They are the universe's ultimate recycling centers. Swirling within them is the entire atomic inheritance of the dead star, a rich mixture of hydrogen and helium now lavishly enriched with oxygen, carbon, iron, silicon, and gold. This is the stardust that will form everything to come, and within these nebulae, the great cycle begins anew. The subtle, relentless pull of gravity starts its work again, drawing denser patches of this enriched gas together. These knots collapse, heat up, and eventually ignite, giving birth to a new generation of stars. But these are not the first pure stars of the early universe. This new generation is born with a profound advantage. They are already surrounded by the heavy elements needed to form so much more than just a star. As a new star like our Sun flares to life at the center of such a cloud, the leftover material in the surrounding disk begins to clump together. Tiny particles of dust, specks of iron, and flecks of rock rich in silicon and oxygen stick to one another. They form pebbles, then rocks, then planetesimals, and finally, full-fledged planets. This is how our own solar system was born, from the ashes of one or perhaps several of these ancient stellar explosions. The iron that makes up the core of our planet, the silicon in the rocks beneath our feet, the oxygen in our air, and the carbon in every living cell on Earth, all of it was forged in the heart of a massive star that lived and died billions of years before the Sun even existed. You are not just living on a planet, you are living on a monument to a cosmic catastrophe, assembled from the recycled remains of a long-dead star. Our own Sun carries the chemical memory of that ancient violence. It is not a first-generation star born from the pristine hydrogen and helium of the Big Bang. Our Sun is a third-generation star, a product of cosmic recycling on a grand scale. It condensed from a cloud of gas and dust that was already rich with the ashes of at least one, and likely several, previous supernova explosions. The evidence for this is all around us and, in fact, within us. Every rocky planet, every metallic asteroid, and every living cell in our solar system is built from elements that were forged in the hearts of those long-dead stars. A star composed only of hydrogen and helium could never have formed a system like ours. It would have no silicon to make rocks, no iron to make planetary cores, no oxygen to form water, and no carbon to serve as the backbone of life. The very existence of the Earth, with its complex geology and rich chemistry, is direct proof of our Sun's explosive heritage. This means the violent death of a massive star was not just a distant cosmic event, it was a necessary prerequisite for our world to exist at all. The specific blend of elements we find here, from the gold in a mountain to the calcium in your bones, tells a forensic story of our local cosmic history. It is a history written in atomic code, a testament to the creative destruction that forged our galactic neighborhood and ultimately made our life-bearing planet possible. That stardust, rich with the legacy of ancient stars, now began its final transformation into worlds. As the young Sun blazed to life at the center of the swirling nebula, its heat created a dramatic temperature gradient across the protoplanetary disk. Close to the newborn star, the environment was a furnace. Only the most resilient materials, the ones with the highest melting points, could survive as solid particles. Think of it as a cosmic sorting process. Volatile gases like water and methane were blasted away from the inner system, but the hardy remnants of supernova remained. Microscopic grains of iron, along with compounds of silicon, magnesium, and oxygen, the very ash of stellar furnaces, began to condense out of the cooling gas. These were the first solid seeds of future planets. In a delicate dance governed by static electricity and gentle collisions, these microscopic particles began to stick together. Dust grains became pebbles, pebbles clumped into larger rocks, and rocks, over thousands of years, coalesced into mountain-sized bodies called planetesimals. This was the era of accretion, a grand construction project on a scale we can barely comprehend. These planetesimals, themselves composed of stardust, then began a gravitational dance, colliding and merging in spectacular impacts that released immense energy. Through this violent and chaotic process, they swept up most of the available material in their orbital paths, eventually forming the 4 terrestrial planets we know today: Mercury, Venus, Earth, and Mars. Each of these worlds is, in its essence, a massive collection of ancient stellar debris. The iron that sank to form Earth's core, the silicon and oxygen that built its rocky mantle, all of it was once scattered across light years of space. This accretion process did more than just build spheres of rock. It created stable, lasting platforms. For the first time, the diverse elements forged in different stellar environments were brought together and held in close, permanent proximity. On the surface of these new worlds, particularly one at just the right distance from its star, these elements could now interact. Chemistry, no longer confined to the thin gases of space, could become truly complex. The stage was now set for the next, and perhaps most fragile, act in the cosmic story. Our young Earth was a scorching, molten sphere, a world of rock and metal utterly devoid of water. The very ingredients needed for oceans and life could not have survived the intense heat of the inner solar system during its formation. The water that fills our seas and the complex carbon-based molecules that form the foundation of life had to come from somewhere else. Their arrival was a gift from the distant, frozen reaches of our newborn planetary system, far beyond the orbit of Mars, where the sun's warmth was only a faint memory. The protoplanetary disk was a deep freeze. Here, temperatures were so low that volatile compounds like water, ammonia, and methane could exist as solid ices. These ices mixed with the same dusty stardust that built the inner planets, coalescing into vast populations of icy bodies, comets, and asteroids. These objects became the solar system's natural supply ships, carrying the precious cargo of volatiles locked within their frozen hearts. For hundreds of millions of years, the solar system was a chaotic shooting gallery. The gravitational influence of the giant planets, particularly Jupiter, destabilized the orbits of countless comets and water-rich asteroids from the outer disk, flinging them inward on collision courses with the inner planets. This era, known as the Late Heavy Bombardment, was a time of apocalyptic violence for the young Earth. The sky was frequently lit by incoming fireballs, and the planet shuddered under the force of immense impacts that carved out vast craters and churned the newly solidifying crust. Yet this celestial barrage was also a creative deluge. With every icy comet and carbonaceous asteroid that struck, it released its trapped volatiles into the primitive atmosphere. Comets, often described as dirty snowballs, delivered enormous quantities of water ice. Asteroids, particularly a class known as carbonaceous chondrites, were even more crucial, as they brought not only water but also a rich inventory of prebiotic organic molecules, including amino acids and nucleobases, the very building blocks of proteins and DNA. This violent rainfall of ice and rock transformed a barren, hellish world into a planet ripe with potential. The water vapor released from countless impacts condensed and fell as rain for millennia, slowly filling the low-lying basins to create the first primitive oceans. At the same time, the complex organic molecules they carried were scattered across the planet's surface, dissolving into these newly formed seas. The Earth's early oceans were not just water, they were a dilute primordial soup, rich with the chemical ingredients for life, all delivered from the depths of space. The transition from a sterile rock to a living world required this specific sequence of events: the forging of elements in stars, the assembly of planets from that stardust, and finally, the delivery of life's solvents and building blocks by the very same celestial impacts that once threatened to sterilize the planet. The violence of cosmic collisions and the gentle chemistry of life are not opposites, they are two chapters in the same incredible story. That iron core, forged in stellar furnaces and delivered by ancient impacts, became the beating heart of our planet. While the surface cooled into a solid crust, Earth's interior remained a roiling, molten engine. The immense quantity of iron, far heavier than the surrounding rock, sank to the very center, forming a dense metallic core. This was not a one-time event. The core remains a dynamic, seething ocean of liquid iron, kept molten by two powerful heat sources. The first is the primordial heat left over from the planet's violent formation, the energy of 1 trillion cosmic collisions. The second is a more patient, persistent fire, the heat released by the radioactive decay of elements like potassium, uranium, and thorium. Every one of these atoms was itself forged in a supernova explosion, meaning the energy that powers our planet's heart is a direct inheritance from a star's death. This internal heat sets the entire core in motion through a process called convection. Hotter, buoyant liquid iron rises from the depths, while cooler, denser iron near the top sinks back down, creating a planet-wide system of churning currents. And it is this motion of a conductive liquid metal that generates Earth's global magnetic field, the magnetosphere. This invisible force field extends thousands of kilometers into space, acting as a planetary shield. The Sun constantly emits a stream of charged particles, the solar wind, which would otherwise slowly but surely erode our atmosphere, stripping it away molecule by molecule into the void. Our magnetic field deflects this relentless assault, channeling the particles harmlessly toward the poles where they create the beautiful auroras. Without this protective barrier, Earth would have suffered the fate of Mars, a world that lost its global magnetic field, and with it, most of its atmosphere and surface water. The very existence of our thick, life-sustaining air and the stable climate it provides is a direct consequence of that churning, supernova-born iron core. The same element that signaled a star's death became the ultimate guardian for life on Earth. A new world was taking shape, one defined by the interaction of rock, water, and air. As Earth's molten surface finally cooled enough to form a solid crust, its seething interior began to breathe. Volcanoes, countless and furious, pierced the young landscape, spewing forth gases that had been trapped deep within the planet's mantle for eons. This process, known as outgassing, filled the skies with a thick, primitive atmosphere, a toxic brew of carbon dioxide, nitrogen, and water vapor, utterly unbreathable to us, but a vital starting point for everything to come. At the same time, the water delivered by millions of cometary and asteroid impacts could no longer remain as steam. It condensed from the cooling air and fell from the sky in an epic, planet-wide rainfall that may have lasted for millions of years, slowly filling the vast lowlands and carving the first riverbeds. The birth of the oceans was a monumental event, transforming Earth from a scorched rock into a world divided between land and sea. Now the stage was truly set. The atmosphere and the oceans became the universe's grandest chemistry sets. The air, rich with carbon dioxide, dissolved into the warm waters, while nitrogen accumulated overhead. Lightning strikes provided sudden jolts of energy, and the relentless heat from the young sun bathed everything in ultraviolet light. In the deep ocean vents, superheated water laden with minerals from the crust mixed with the chemicals from space. These environments were not just containers, they were immense planet-scale reactors where the elements forged in stars could finally meet, mingle, and combine in an infinite number of ways. This was the crucial bridge between the non-living and the living, the moment when stardust, having journeyed across space and time, found itself in a stable, nurturing environment where it could begin the most fragile and complex of experiments, the organization of matter into life itself. Carbon is the silent architect of life, a master builder with a unique talent for connection. Its power lies in its atomic architecture. A carbon atom has 4 connection points, allowing it to form strong, stable bonds with up to 4 other atoms at once. This simple, brilliant design enables a miracle of construction called catenation, the ability for atoms to link together in long chains and intricate rings. Think of carbon atoms as universal Lego bricks with 4 studs on all sides. They can build straight scaffolding, curved loops, and complex 3-dimensional structures of almost limitless variety. This is the foundational geometry of every complex molecule in your body. It is how we get the long, folded chains of amino acids that build proteins, the exquisite double helix of DNA that encodes genetic information, and the ringed sugars that provide energy. No other element in the periodic table possesses this same effortless versatility for creating such a vast and stable library of structures, but carbon's genius does not end with its shape. The molecules it forms are remarkably durable across a wide range of temperatures, especially the moderate conditions found on a planet like Earth. They are stable enough to maintain their structure, yet reactive enough to engage in the complex dance of metabolism. This chemical stability is as vital as its structural flexibility. And then there is the matter of abundance. Carbon is not a rare cosmic treasure. It is the 4th most common element in the entire universe, a direct product of the triple alpha process in countless red giant stars. This universal prevalence meant that when the Earth formed and cooled, carbon was already here in great quantity, dissolved in the oceans and scattered across the landscape. The chemistry of life was not waiting for a rare ingredient to arrive. The universe had already produced the perfect, versatile, and plentiful building block in staggering amounts. Given a stable planet with liquid water and a source of energy, the emergence of carbon-based complexity begins to seem less like a freak accident and more like a natural, almost expected, phase in the evolution of matter itself. Oxygen is the universe's paradox, a destructive force that also unlocks the potential for vibrant, energetic life. Forged in the same stellar furnaces as carbon, this element was destined for a dual role. Its first and most fundamental job is as a structural component of water. Every single biochemical reaction in every known living cell requires a liquid medium to dissolve nutrients, shuttle molecules, and facilitate chemical handshakes. Water, with its 1 oxygen atom bonded to 2 hydrogens, is that perfect universal solvent, and without the oxygen shipped here from a long-dead star, our planet would be a barren desert. But oxygen's second act is even more dramatic. When 2 oxygen atoms bind together, they form the gaseous molecule O2 that fills our atmosphere. This is the key to high-performance life. Simple, single-celled organisms can get by on inefficient, anaerobic processes, but to power a beating heart, a running animal, or a thinking brain, you need a far more potent energy source. Aerobic respiration is that powerhouse. It is essentially a slow, controlled burn of fuel, using atmospheric oxygen to break down food molecules and release their stored energy. This process generates nearly 20 times more energy than its anaerobic counterpart. Think of the difference between a smoldering ember and a roaring fire. That immense energy surplus is what fuels the complexity of multicellular organisms, allowing for specialized organs, sophisticated nervous systems, and the very capacity for conscious thought. Yet this life-giving atmosphere was not a foregone conclusion. For over 2 billion years, Earth had virtually no free oxygen. The transformation began with tiny, unassuming cyanobacteria in the ancient oceans. These microscopic pioneers discovered how to use sunlight to split water molecules, a process called photosynthesis that produces oxygen as a waste product. They were so successful that they began to flood the planet with this reactive, toxic gas, triggering the Great Oxidation event. This was a planetary catastrophe for the anaerobic life that existed at the time, but it was an event made possible only because the raw ingredient, the oxygen atoms themselves, were already here. The cyanobacteria were simply the mechanics who turned on the engine, but the engine itself, the element oxygen, was built in a star. Life learned to harness a tool that the cosmos had already provided, setting the stage for everything that was to come. These trace elements are the silent conductors of the body's symphony. While carbon, oxygen, and nitrogen form the main structure of our cells, these rarer atoms are the master regulators that make everything work. The most famous of these is iron, forged in the final moments of silicon fusion just before a star's core collapses. This metal is not merely present in our bodies, it is absolutely essential for our survival. At the core of every hemoglobin molecule in your red blood cells sits a single, carefully caged iron atom. This atom has a unique and vital talent. It can temporarily bind to an oxygen molecule. As your blood travels through your lungs, these iron atoms each grab a passenger of oxygen. Then, as the blood circulates to the farthest reaches of your body, to the muscles in your fingertips or the neurons in your brain, they release that life-giving cargo. Without that supernova-forged iron atom at the center of it all, oxygen would simply dissolve in your blood, unable to be delivered to the tissues that desperately need it. You would suffocate from within despite breathing air. This is why anemia, a deficiency of iron, causes such profound fatigue. Your body's power distribution system is failing. Then there is iodine, an element born in the frantic chaos of the Are process during a supernova. Your body needs only a minuscule amount, but that tiny quantity is concentrated in your thyroid gland. Here, iodine atoms are incorporated into hormones that act as the master control for your metabolism. They regulate how quickly you burn energy, how fast your heart beats, and even how your brain develops in childhood. An iodine deficiency can lead to a swollen thyroid gland, profound lethargy, and in severe cases, cognitive impairment. The difference between vibrant health and serious illness can hinge on the presence of a few atoms that were created in a stellar explosion billions of years ago. The list goes on. Zinc, another gift from supernova, is a crucial partner for over 300 different enzymes, the proteins that catalyze chemical reactions in your body. It helps with wound healing, immune function, and even your sense of taste and smell. Copper is essential for building connective tissue and for enabling your nerves to communicate. Selenium protects your cells from damage. These elements are not optional extras. They are fundamental components of the intricate machinery of life. Your body is a living testament to the entirety of the periodic table. Every single element, from the most abundant to the rarest trace, plays a specific and irreplaceable role. The universe did not just provide the bulk construction materials, it supplied the entire toolbox, down to the most specialized wrenches and screws, all forged in the hearts of stars and their violent deaths. This cosmic story is written in the very light of the stars. We know the details of this grand narrative not from ancient texts, but from a powerful scientific technique called spectroscopy. Think of it as the universe's ultimate forensic tool. When we point a telescope at a star, we are not just collecting its light, we are capturing its unique chemical identity. Every element in a star's outer atmosphere leaves a distinct signature on that light, a set of dark lines imprinted on the rainbow-like spectrum. It is an atomic barcode. By carefully reading these barcodes, astronomers can determine precisely which elements are present in a star and in what quantities. This single method allows us to perform stellar archaeology, digging into the chemical past of our galaxy. The evidence it reveals is stunningly clear. The oldest stars we can observe, known as Population 3 stars, are the cosmic pioneers. Their light tells us they are composed almost entirely of hydrogen and helium. They are the pristine relics of a simpler time, formed from the pure, unmixed gases of the early universe before any supernova had a chance to pollute them with heavier elements. Then we look at a star like our own Sun. Its spectral signature is a complex symphony, filled with the distinct lines of iron, oxygen, silicon, and carbon. This rich chemical diversity is the direct result of inheritance. Our Sun was born from a cloud that had already been seeded by the explosions of those earlier, more massive stars. This gradient of chemical richness, what astronomers call metallicity, creates a direct timeline across the galaxy. The oldest stars in the galactic halo are metal-poor, while younger stars in the bustling spiral arms are metal-rich. This is not a random pattern, it is a cumulative record. It is the undeniable forensic proof that the galaxy has been progressively enriched over billions of years, with each stellar generation contributing its own unique blend of elements to the cosmic reservoir. The light from every star is a historical document, and spectroscopy is the language we use to read it, confirming the epic story of our own cosmic origins. The story of cosmic creation, however, had a missing chapter. For decades, astronomers were convinced that supernovae were the sole crucibles for the universe's heaviest treasures. But the numbers did not quite add up. There seemed to be more gold in the galaxy than the most violent stellar explosions could possibly account for. The answer arrived in a spectacular flash of light in 2017. It came not from a single dying star, but from the cataclysmic merger of two of the most extreme objects in existence, neutron stars. This event is known as a kilonova. When these unimaginably dense stellar corpses, each more massive than our Sun yet crushed into a city-sized sphere, spiral into each other and collide, they unleash a firestorm of creation that dwarfs even a supernova. The violence of the impact blasts a significant fraction of their material into space. This ejected cloud is not just hot, it is neutron-rich beyond comprehension. It is a blizzard of nuclear building blocks. Within this expanding shrapnel, the rapid neutron capture process, the Are process, finds its ultimate playground. Atomic nuclei are bombarded by such an intense, dense wave of neutrons that they cannot help but swell. They gulp down dozens of neutrons in mere seconds, transforming into grotesquely overweight, unstable versions of themselves. These bloated nuclei then rapidly decay, settling into the most stable forms of the heaviest elements in the periodic table. The 2017 event was a scientific milestone. For the first time, telescopes trained on the aftermath of a neutron-star merger did not just see a flash of light. They saw the unmistakable spectroscopic signature of freshly forged elements. The light was redder and lasted longer than a supernova's glow, and its changing color over days revealed the radioactive decay of enormous quantities of heavy metals, including an amount of gold with a mass greater than that of our entire planet. This single collision produced enough precious metals to load every asteroid in a large star system. Kilonovae are now understood to be the universe's primary forges for elements like gold, platinum, and uranium. This revelation adds a breathtaking new layer to our origins. The gold in a wedding ring or a microchip is not just stardust, it is the direct ash from one of the most violent and rare dances in the cosmos, the final embrace of two dead stars. This single carbon atom began its existence in a flash of cosmic necessity. It was born from a frantic, three-way collision inside a red giant star that lived and died long before our sun was even a glimmer in a nebula. In that stellar forge, 3 helium nuclei, themselves remnants of an earlier hydrogen-burning era, slammed together in the triple alpha process, and a new, stable carbon nucleus flickered into being. It was the original act of creation for a journey spanning billions of years. When its parent star eventually went supernova, the atom was violently ejected, cast out into the interstellar void like a seed on a cosmic wind. For eons, it drifted in the cold, dark silence of a vast nebula, a mere speck of stardust amidst a swirling cloud of other elemental ashes. Then, a shock wave from a nearby stellar explosion or the gentle tug of gravity began to pull the cloud together, and our carbon atom was swept up into the collapsing material that would one day become our entire solar system. It was here, in the protoplanetary disk swirling around our infant sun, that its journey took a new turn. The atom found itself bound to oxygen, forming a carbonate mineral that became part of a solid rock on the young, molten surface of the Earth. For millions of years, it lay buried deep within the planet's crust, until the slow, inexorable motion of tectonic plates dragged that rock down into the searing heat of the mantle. There, the intense pressure broke its chemical bonds, and the carbon atom was released, joining with oxygen to become a molecule of carbon dioxide gas. It then rode a plume of superheated magma upward, escaping through a volcanic vent in a tremendous eruption that returned it to the atmosphere. It circulated in the air until it was drawn into the leaf of a prehistoric fern. Captured by the miracle of photosynthesis and with energy from sunlight, it was incorporated into a simple sugar molecule, a molecule of glucose. That plant was then consumed by a grazing dinosaur, and the atom became part of the great beast's body, perhaps fueling a single muscle contraction as it walked through a steamy Jurassic forest. After the dinosaur's death, its body decomposed, and the atom was recycled through the soil, taken up by other plants, and passed through countless organisms over millennia. It moved through an unbroken chain of life and death until one day, it was woven into a nucleotide and became a permanent part of a DNA molecule, a tiny section of the genetic code inside one of the cells in your body. The same atom that was forged in the heart of a distant star now helps define your unique biological identity. Its epic voyage connects the violent death of a star to the gentle beating of your own heart. This cosmic fine-tuning leads to a profound and almost unsettling question. Why does the universe appear so perfectly set up for our existence? The physical laws and constants seem suspiciously hospitable. If the force of gravity were even slightly stronger, the universe would have collapsed back on itself long ago. If it were slightly weaker, galaxies and stars would never have formed at all. This apparent perfection extends directly into the heart of stellar nucleosynthesis. The very existence of carbon, the backbone of life, hinges on a breathtakingly precise nuclear resonance. When three helium nuclei collide in a star to form carbon, the energy levels inside the new carbon nucleus align with near miraculous accuracy. This resonance acts like a perfectly tuned key, unlocking the reaction and making carbon production incredibly efficient. Without this specific, finely tuned energy level, the triple alpha process would be a dead end, and the universe would be devoid of carbon-based life. The plot thickens with oxygen. The same process that creates carbon could easily destroy it, as a carbon nucleus can fuse with another helium nucleus to form oxygen. Yet here, the energy levels are just wrong enough. There is no strong resonance to facilitate this reaction, creating a delicate balance. Stars produce an abundance of carbon without immediately converting all of it into oxygen. This nuclear tightrope walk ensures that the universe ends up with plenty of both carbon for structure and oxygen for water and energy. It is a cosmic recipe that seems meticulously calibrated. These observations form the basis of the Anthropic Principle, a philosophical idea that confronts the sheer improbability of it all. In its simplest form, it suggests the universe must have properties that allow life to arise because we are here to observe it. Our very existence acts as a selection effect. We could not possibly be asking these questions in a universe that was not capable of producing us. Some interpret this as evidence for a deeper design, a universe built with intention. Others propose a more statistical answer, the concept of a multiverse. In this view, our universe is just one of a vast, perhaps infinite, number of parallel realities. Each has its own random set of physical constants and laws. In the overwhelming majority of these universes, the numbers do not line up, stars do not form, or they produce no carbon, and those realities remain forever dark and lifeless. But in a tiny, statistically inevitable fraction, the constants fall into the perfect Goldilocks zone, and conscious observers emerge to wonder at their own luck. Whichever interpretation resonates with you, the underlying truth remains the same. The path from the Big Bang to a living, breathing human is paved with a long chain of cosmic coincidences, each one dependent on the last. The death of stars was not just a random act of violence. It was a necessary, precisely engineered step in a chain of events so fragile and so specific that our entire existence hangs upon it. We are not merely living in the universe, we are a manifestation of its most intimate and finely balanced secrets. This universal recipe for life has profound consequences for our place in the cosmos. If the elements for life are forged in stars and scattered by their explosive deaths, then these raw ingredients are not unique to Earth. They are a common byproduct of stellar evolution, a kind of cosmic contamination that must have seeded countless other worlds throughout the galaxy. This fundamental insight transforms the search for extraterrestrial life from a question of possibility into a question of probability. We now possess direct evidence that the universe is teeming with potential homes. Powerful telescopes have confirmed the existence of thousands of exoplanets, many of them rocky, Earth-sized worlds orbiting their stars within the so-called Goldilocks zone. This is the region where temperatures are just right for liquid water to exist on the surface, a condition we believe is crucial for chemistry to become biology. These distant planets are not made of some exotic alien substance. They are constructed from the very same stardust as our own world, the same iron, silicon, oxygen, and carbon that assembled our solar system. They are, in essence, siblings of Earth, born from the same galactic recycling process. This means the basic chemical toolkit for life, the entire periodic table required for proteins, DNA, and cell membranes, is available on a cosmic scale. The universe has been conducting the same grand experiment in countless other laboratories. The specific forms that life might take on these worlds are beyond our imagination. It could be based on a different biochemistry, or it might look nothing like the life we recognize, but the foundation, the elemental building blocks, are a universal constant. This shifts the entire paradigm of astrobiology. We are no longer searching for a needle in a haystack, but rather, we are walking through a field where the conditions for needles are everywhere. The great silence of the cosmos may not be a sign of emptiness, but a testament to the vast distances and timescales involved. Every time we look up at the night sky, we are not just looking at points of light. We are looking at potential factories for worlds, and perhaps for other beings looking back, all of us connected by the shared inheritance of ancient stardust. The cosmic clock ticks with a patience that defies all human experience. The entire timescale of human civilization, from the first cities to the internet, is a mere blink in the epic saga of element creation. After the Big Bang, the universe waited in darkness for nearly 200 million years before gravity could gather the first stars. These pioneers were behemoths, and they lived fast and died young, burning through their nuclear fuel in just a few million years. Their spectacular deaths were the first crucial deliveries of heavy elements, but the process was just beginning. Our own sun is a testament to this slow, cumulative build-up. It has been fusing hydrogen for 4.6 billion years, a span of time so vast it encompasses the entire history of life on Earth, from the first single-celled organisms to the rise of humanity. Consider this: the iron in your blood was likely forged in a star that died over 5 billion years ago. It then drifted in space for eons before our solar system even coalesced. It took another 4.5 billion years for that iron atom to become part of you. This grand, multi-billion-year timeline is not a background detail, it is the central character of the story. We are the product of this immense cosmic patience. Every human life is a fleeting moment, a brief spark that glows for an instant against a backdrop of unimaginable eons. We are not just made of stardust, we are a whisper of consciousness from an ancient flame that took its time to learn how to build. Our own star, the Sun, holds a quiet, inevitable fate. In approximately 5 billion years, the last of the hydrogen fuel in its core will finally be consumed. The delicate balance between gravity and radiation pressure will shatter for the final time. Without the outward push from fusion, the Sun's own immense weight will begin to crush its core, forcing it to contract and heat up dramatically. This surge of heat will ignite a last, desperate blaze, pushing the Sun's outer layers outward with irresistible force. Our familiar yellow star will swell into a monstrous red giant, its bloated atmosphere expanding to engulf the inner planets. Mercury and Venus will be vaporized, and the Earth's surface will be scorched into a molten wasteland. This is not the end of the story, however, but the beginning of a beautiful and poignant transformation. After a relatively brief period as a red giant, the Sun will become unstable. It will pulse violently, eventually casting off its entire outer envelope into space. This expelled shell of incandescent gas will expand, illuminated from within by the hot, exposed core of the star. What was once our Sun will have become a planetary nebula, a glowing, intricate veil of cosmic gas that will shine for tens of thousands of years. This nebula will be rich with newly forged elements, a final gift to the galaxy. During its red giant phase, the Sun's core will have become hot enough to fuse helium into carbon and oxygen through the triple alpha process. As the star sheds its layers, it scatters these life-essential atoms back into the interstellar medium. The carbon that once burned in its heart, the oxygen it created, all of it is returned to the cosmic reservoir from which it came. Left behind at the center of this glowing nebula will be the Sun's core, exposed and inert. No longer supported by fusion, it will collapse under its own gravity into an incredibly dense object known as a white dwarf. This stellar remnant will contain roughly half the original mass of the Sun, but compressed into a sphere no larger than the Earth. A single teaspoon of its material would weigh many tons. For trillions of years, this white dwarf will slowly radiate its residual heat away, fading from white to yellow to red, and finally to a cold, black cinder in the darkness. While our Sun is not massive enough to die in a supernova, its quiet demise is no less vital to the grand cycle. It dutifully returns its enriched material to the galaxy, contributing its own unique blend of carbon and oxygen to the cosmic mix. This material will one day drift into a vast, cold molecular cloud. Millennia later, that cloud may collapse under the gentle persuasion of gravity, giving birth to a new generation of stars and planets. Those future worlds will form from stardust that once belonged to our Sun, carrying the potential for new oceans, new continents, and perhaps new life. The end of our solar system is not merely a destruction, but a dispersal, a promise that the atoms which once gave us light and life will one day become part of something new. This connection is a physical reality written into your very cells. The calcium that strengthens your bones was created in the last furious moments of a massive star's life, fused from oxygen and silicon just before the core collapsed. The phosphorus that forms the backbone of your DNA, the molecule that holds your genetic code, was likely forged in the same supernova explosion. Every time you take a breath, you inhale oxygen atoms that were once the outer atmosphere of a red giant star. When you cut yourself and see a drop of blood, the iron that gives it that vivid red color is the same element that spelled doom for a stellar core billions of years ago. You are a walking, talking collection of cosmic artifacts. This idea transforms our sense of self and our place in the cosmos. We often feel small and separate when we look up at the night sky, but the truth is far more intimate. The same nuclear forces that light the stars beat within your own heart. The same ancient cycles of creation and destruction that built galaxies are the reason you are here to ponder them. We are not passive observers of the universe. We are the universe itself become conscious, looking back at its own origins and wondering how it all came to be. Your body is a temporary gathering of atoms that have embarked on an epic journey across space and time, a journey that began in the heart of a star and for a little while has come together to form you. These microscopic flecks of cosmic soot and sand are far more than just dust. They are the universe's ultimate construction workers, silently assembling the foundations for worlds and the chemistry for life itself. Floating in the vast, cold emptiness between stars, these tiny grains, smaller than a wavelength of light, are primarily made of silicates, the same stuff that makes up sand on a beach, and carbon compounds, the essential scaffolding of biology. Their first, and perhaps most crucial, job is to solve a fundamental problem. In the near-perfect vacuum of space, it is incredibly difficult for two lone hydrogen atoms to meet and stick together to form molecular hydrogen, the primary fuel for star formation. The dust grain provides a perfect solution. It acts as a microscopic dance floor, a solid surface where two hydrogen atoms can land, slow down, and eventually link up. Without these tiny catalysts, the great clouds of gas that birth stars would struggle to cool and collapse, stalling the entire cosmic cycle before it could even begin. Once a new star like our Sun ignites, the role of dust becomes even more dramatic. Within the swirling, flattened protoplanetary disk, these microscopic particles are the seeds of planets. They are the initial specks that begin to collide and stick together, not through forceful impacts but through gentle, static electric embraces. Think of a dusty room where sunbeams highlight countless motes floating in the air. Now, imagine that room is light years across, and every single one of those motes is a potential building block for an entire world. These tiny grains grow into pebbles, the pebbles gather into rocks, and the rocks, through countless collisions, eventually form the mountain-sized planetesimals that gravity will sculpt into planets. The very ground beneath your feet, the core of the Earth, and the mountains of Mars all began as insignificant specks of interstellar dust, the discarded ashes of long-dead stars. But the most profound role of dust may be its function as a nursery for life's ingredients. Deep in the cold, dark molecular clouds that predate solar systems, a faint, telltale signature appears in the data from infrared telescopes. This signal reveals the presence of complex organic molecules known as polycyclic aromatic hydrocarbons, or PAHs for short. These are not simple gases. They are large, sturdy, carbon-based molecules with structures that look like tiny segments of chicken wire. They are found coating the surfaces of these interstellar dust grains. The existence of PAHs in such hostile environments is a staggering revelation. It means that the first steps toward the chemistry of life, the formation of complex, carbon-rich structures, is not a process that waits for a warm, watery planet. It begins out here in the freezing darkness of deep space on the surfaces of these ubiquitous dust motes. These grains act as protected workshops, shielding fragile molecules from destructive stellar radiation and providing a solid surface where atoms can meet and link into ever more complex arrangements. The dust is not just building planets, it is pre-loading them with the potential for life itself, sowing the cosmic clouds with the raw chemical code for biology long before a star system is even born. Yet even the simplest story from the Big Bang holds a lingering, unresolved mystery. The universe's first few minutes should have left a very specific amount of lithium scattered among the primordial hydrogen and helium. The calculations are precise and elegant, born from our deepest understanding of nuclear physics and cosmology. But when we point our telescopes at the most ancient stars in the galaxy, the pristine relics of the early cosmos, the numbers do not match. These old stars contain only about 1/3 of the lithium that our theories insist should be there. This glaring discrepancy is known as the cosmological lithium problem, and it is a quiet but persistent thorn in the side of modern astrophysics. Where did all that primordial lithium go? One compelling possibility is that our models of the infant universe, while incredibly successful, are still missing a small but crucial piece of physics. Perhaps an unknown particle or a subtle interaction we have not yet accounted for altered the nuclear reactions in those first 3 minutes. The other leading suspect is the stars themselves. Even these ancient metal-poor stars are not completely inert. They have interiors, and processes within them could have slowly destroyed that fragile lithium over billions of years. Certain nuclear reactions occurring just beneath a star's surface might have acted like a cosmic filter, scrubbing away the lithium that was originally there. This puzzle is a powerful reminder that our map of cosmic history is not yet complete. The very first chapter of elemental creation, the one we thought we understood best, still holds a profound secret, waiting for a future observation or a flash of theoretical genius to finally reveal the truth. These fleeting blasts of pure energy are the universe's most powerful sirens. Gamma-ray bursts are not the explosions themselves, but the brilliant, focused beacons that signal an event of almost incomprehensible violence. For a few seconds, a single gamma-ray burst can outshine every star in 1,000,000 galaxies combined. Its light focused into a pair of narrow, relativistic jets that scream across the cosmos at nearly the speed of light. The source of this fury is the death of the most massive stars in the form of a hypernova, or the final shattering collision of two neutron stars. This is the crucible where the rapid neutron capture process, the R process, finds its most potent and prolific expression. The environment within these jets is unlike anything else in nature, a maelstrom of energy, radiation, and particle density so extreme that atomic nuclei are forged in an instant. The sheer power of these events does more than just create heavy elements. It acts as a cosmic cannon, blasting this newly forged atomic wealth out of its host galaxy and into the vast intergalactic medium. A single gamma-ray burst could be responsible for enriching millions of future galaxies with the seeds of planets and life. For decades, these bursts were just mysterious flashes on military satellites, their origins a total enigma. Today, we understand they are our most direct window into the real-time creation of the heaviest elements. When a gamma-ray burst fades, it leaves behind a lingering afterglow that can be studied across the electromagnetic spectrum. It is in the specific colors and the gradual dimming of this afterglow that astronomers find the forensic evidence, the spectral signatures of freshly synthesized gold, platinum, and uranium. These events are so powerful and so efficient that they may be the primary source for all the gold in the universe, turning the most catastrophic stellar deaths into the ultimate cosmic foundries. They are the great distributors, ensuring that no corner of the cosmos remains forever impoverished, that the raw materials for complexity are sown far and wide, connecting the fate of one dying star to the potential of countless worlds yet to be born. Our modern periodic table is a living chronicle of deep time. It was not always this rich and complex tapestry of elements we see today. In its earliest form, merely minutes after the cosmic dawn, it was a stark and simple list of just 3 entries: hydrogen, helium, and a trace of lithium. For the next several hundred million years, that was it. The universe's chemical library was virtually empty, containing only the barest foundations. Nothing could be built from such a limited palette. Then the first stars switched on, and the long, slow process of cosmic enrichment began. With the birth and death of that initial generation, new boxes on the table were permanently filled. The stellar forges created carbon and oxygen, the fundamental elements for life and water. Later stars, building on the ashes of their predecessors, added neon, magnesium, silicon, and sulfur. Each stellar generation contributed its own unique signature, a new set of elements forged in its specific type of furnace, but the table was still incomplete. The final, heaviest elements, from iron upward, required the most extreme violence of all. It was the supernova explosions and, we now know, the spectacular collisions of neutron stars that filled in every remaining box. Gold, uranium, iodine, all were minted in these final, catastrophic acts. This means the periodic table is not a static chart but a dynamic historical document. It maps the entire 13.8 billion-year evolution of matter, from the primordial fireball to the complex chemistry that builds planets and life. The universe started with a whisper of simplicity and, through stellar alchemy, built itself into the breathtaking complexity we see today. But how can we possibly know what happens inside a star? The answer lies not just in our telescopes, but in our laboratories. Here on Earth, scientists are recreating the very fires of creation to test every detail of this cosmic story. They use immense machines called particle accelerators, which act like cosmic cannons. These devices hurl atomic nuclei at each other at nearly the speed of light, simulating the frantic, high-energy collisions that occur deep within a stellar core. By meticulously measuring the outcomes of these tiny, man-made explosions, physicists can determine the exact probabilities and rates of the nuclear fusion reactions that power stars. This crucial data tells us how quickly a star burns its fuel, how long it will live, and which elements it can produce. Another powerful tool involves focusing enormously powerful lasers onto a tiny speck of material. In a flash lasting just billionths of a second, these lasers can generate temperatures and pressures that rival the heart of a supernova. For that fleeting moment, scientists can observe matter behaving as it does only in the most violent cosmic events. This entire field of research is known as laboratory astrophysics. It bridges the immense gap between astronomical observation and fundamental physics. The abstract equations and theoretical models that describe stellar furnaces are no longer just elegant ideas on a blackboard. They are now grounded in hard, reproducible data measured under controlled conditions. Every new measurement from these experiments helps refine our computer simulations of stars and their explosive deaths, making our story of cosmic origins more precise and more certain with every passing year. This realization carries a philosophical weight as profound as the science itself. Knowing you are stardust shatters the old idea that we are separate from the cosmos, visitors in a cold and indifferent universe. The truth is far more intimate. You are not just living in the universe, you are a mode through which the universe experiences itself. The same law of gravity that orchestrates the majestic dance of galaxies is the very force that anchors your feet to the ground. The nuclear strong force that holds an atomic nucleus together against impossible pressure is the same energy that once burned in a star's heart and now powers the cells in your body. There is no distinction between the cosmic and the personal. This knowledge often arrives as a dual feeling, a deep humility and an immense connection. The humility comes from understanding our scale, that we are temporary gatherings of ancient atoms on a tiny rock orbiting an average star. Yet the connection is even more powerful, tying our fleeting existence directly to the grandest narratives of time and space. We are not an accident on the edge of something vast. We are the universe becoming conscious, turning its gaze back upon itself to ask how it came to be. Every question we ask about a distant nebula or a dying star is, in the end, a question about our own origins. Every discovery in astrophysics adds another verse to the story of our own creation. In this light, our curiosity is not just a human trait. It is the cosmos awakening to its own nature, using our minds as its instrument to comprehend its own beautiful and violent history. From the primordial fire of the Big Bang to the violent death of massive stars, this is the story of a billion-year alchemy. We have traced the incredible journey from simple hydrogen and helium to the rich chemistry that builds our world and our very bodies. Every element, from the iron in your blood to the calcium in your bones, carries the echo of a cosmic cataclysm. This narrative does more than explain where our atoms came from. It forges a profound connection between us and the most dramatic events in the cosmos. You are not a passive inhabitant of this universe, simply living on a random planet. You are the universe itself become conscious, looking back at its own origins and wondering how it all came to be. The same forces that shape galaxies are at work within you. If this journey through cosmic history has sparked your curiosity, we would love to hear your thoughts in the comments below. For more deep dives into the mysteries of space, be sure to subscribe.